Hello, everybody. Thank you for joining us on our webinar today, Flex in Focus, Designer's Guide to Flexible PCBs. Always a very highly interested topic is flex design. I want to introduce our two speakers. So first is Lauren Waslick, PCB Design Director at Newgrange Design. So Lauren is the PCB Design Director. She's also a senior PCB designer with over 12 years of experience. She runs the PCB design department, which includes over 25 designers, and also oversees their training program. She works at a service bureau for 12 years, and it's allowed her to gain extensive experience across many industries, including medical, consumer products, defense, aerospace, alternative energy, robotics, and more. She specializes in flex design, hence presenting this topic, as well as HDI and high speed, and has worked on hundreds of circuit boards in her career. In 2019, she received her MBA from Babson College. So welcome, Lauren. Thank you for joining us. And then later on, we'll be getting a tool demo from Matthew Harms. Matthew is the Applications Engineer Team Leader at EMA. Matthew is an electrical engineer from Canada and has been with EMA as an Applications Engineer since 2003 and is the Application Engineer Team Leader since 2018. At EMA, Matthew specializes in design side issues pertaining to part management, circuit simulation, signal integrity, power integrity, but is conversant in all facets of ECAD design, as well as flex as well. So with that said, just wanted to thank everyone for joining, and it's going to be a great session. So with that, kick it over to you, Lauren. Thank you.
All right, great. Thank you, Chris. And thank you, EMA, for having me here on this webinar to talk about flex design. So really my goal in this presentation is to just help pass along some of the knowledge I've learned on multiple flex designs over the years, whether you've done a lot of designs in the past that are flex or you are just starting to jump into it. Hopefully you pick up something here that helps you in your next design. So I'm going to go through the different types of flex boards that are out there just to make sure there's an awareness of different styles. And then I'm going to go through the key considerations throughout the flex design process in regards to mechanical, footprinting, placement, rules, and routing. And then just talk about the importance of early flex fabricator involvement and making sure you're starting those conversations early in your process, and then summarize the key takeaways. So just to go over the different types of flex boards, the terminology you might be hearing around flex design. First, there's a strict flex. This is only flex material. There's no other materials, no rigid materials involved in the making of this type of board. Then there's flex with stiffener. You'll see some sort of stiffened regions on that flex there. That's when you have sort of a very small amount of components you need to install, but a very simple circuit. Then there's rigid flex, which is a combination of a full rigid board and a flex. This is most commonly seen when you're taking two rigid boards and replacing a cable with a flex. And then there's combination, which really just covers a mix of all of these different types when you've got multiple arms and things going on. In just over a week, we'll be doing a second webinar on flex where I dive into the details of these different stack-ups a little bit more and the different materials. But just wanted to set the stage for the purpose of this webinar on what the different types of flex design are. And really the first question I ask when I'm working with somebody who's wanting to design a flex is whether or not you really should be utilizing a flex in your design. It exists and it's helpful in certain scenarios, but it's not always going to be helpful. So you want to make sure you really as compared to rigid boards. So that's another thing to take into consideration early in that process. The next is just sort of what stage of development are you in? Specifically in the beginning of a design phase, a prototype phase, the cost and time savings of a rigid board strictly in your system might be worth it, even if you end up respinning down the line to have rigid flex involved. For example, if you were trying to prove out your circuitry and you know you needed two rigid boards combined, connected with a flex. In the beginning of development, when you're doing those two rigid boards, and you're not even sure if the circuitry is working yet, it might be helpful to keep them with a board-to-board connector or a cable plug-in, because if you needed to respin one or the other, if it was connected in a rigid flex, you would have to respin the entire board, respend those 2 to 3 weeks of fab and the higher fab costs. But if you had them as two rigid boards with a connector in between, then you'd be able to quickly respin one or the other and make it much cheaper while you're proving out that circuitry before you decide to integrate the flex directly into the layout. And finally, it's just to flex suit the electrical needs of the design. Specifically when dealing with a high power design or sensitive signals, flex might not be your best choice. Really with flex, you generally want to stick to a 1/3 ounce, a 1/2 ounce copper weight. So if you're dealing with high currents that need to travel across that flex or really sensitive signals that might be impacted by the difference in material from rigid to flex, that may or may not actually suit your design in the long run. So just to make sure to think about all of those items before deciding to start your flex. So next we'll go through just the key considerations throughout the flex design process and how to really set yourself up for success with your flex. So questions you want to ask in the beginning in terms of the mechanical: is the rigid size fixed or can it be adjusted? And is the flex size fixed or can it be adjusted? A lot of times when you involve a flex component, there might be a little bit more option to adjust the size or width or angle of those flex areas. And it's good to really understand in the beginning where your flexibility is with your mechanical, because you might have a trade-off. So having that conversation with the mechanical designer up front, knowing if you have flexibility, will help you come to the most creative solutions during design. The next thing that you would want to know is where are your bend lines for your flex going to be, because you want to work that into your software to make sure you've got the correct via keepouts and placement keepouts built in from the beginning of the design. You don't want to wait too far to figure out really how your flex is bending. And then if there is a stiffener involved, is the size and shape of that stiffener clear? Ideally, it needs to touch multiple edges of the flex, and it should exist in any areas that you have components installed on a flex. So making sure you understand those up front, get it built into the software so that you are able to most efficiently complete your design. Additionally, with mechanical, a few other things to keep in mind is how is this flex going to be installed? There are two really types of installation when you're dealing with flex. There's a dynamic, which means it might bend multiple times. It's not going to be set in stone. But then there's a static flex, which means you bend once, generally lock it into place, and it doesn't move. So if you have a dynamic flex and you know it's going to have to be bent multiple times over and over, you might want to consider making it a bit more robust of a design so that it's less prone to breakage. But when it's a static flex, you might be able to get away with something a little more aggressive since it will be locked into place and not have the extra wear and tear. And then just thinking about the bend radius, again, you want to work with mechanical on this. Depending on how many layers your flex is going to impact your bend radius. So you want to just consult with the IPC standards, and here are some rules of thumb for flex. About 6 times your flex width for a 1 to 2 layer design, and about 12 times the width for a 3+ layer design. Again, this is a really important question to ask in the beginning. How many layers do you need to carry the signals and current that are required of the design, and is it still going to meet your bend radius that's required? So here's just a real world example of when knowing your mechanical restrictions is going to could impact your design. So this was a design I did where there were 2 rigid sections on the left and right, and there was a flex connecting them through the middle, and it was only a 2-layer flex. So we had 1 layer for signals and power and the other layer for ground. And when the board was almost completed, we had the flex layer completely utilized. We had to maximize all of our space there to get our signals and power across. And then there was a design update late in the design where more circuitry was added to both sides of the board, causing additional signals to need to be brought across the flex region. So this scenario, we were a little stuck. What should we do? Well, the bend radius was actually very critical in this design. So adding another layer to carry those signals could have jeopardized that mechanical stability, and it wasn't really an option for us. But luckily, since we had involved the mechanical designer early in the process and did some collaborative problem solving, we figured out we could increase that width of that flex. It wasn't necessarily critical that it was as thin as it was, and we had some room to grow. So we were able to keep it at 2 layers, keep the bend radius as it was, and add those additional signals in there, which really just led to the most efficient solution in this case, instead of adding layers, which might have had ripple effects down the road. Next, I want to talk about footprinting and things to be aware of, how your footprints might look a bit different if they're going to be placed on a flex region. Now, this is specifically footprints that are going to be on a flex board, not on a rigid flex in the rigid area. If it's a rigid flex, the footprints can remain exactly as they would be in a rigid, but when you're placing it on flex on top of a stiffener, there are some modifications you might want to make to just make assembly a bit easier. So first is the surface mount pads generally want to be anchored on at least two sides. So you can see in the bottom images, the flex pads and solder mask are modified in order to allow those pads to stay anchored to the board, and it prevents them from peeling off the board. Next is the cover lay sliver. So with solder mask, you can get away with a much smaller sliver, generally 3 to 4 mils. But with cover lay, based on the material that's used, it generally is closer to a 10 mil sliver, which for a lot of surface mount footprints is difficult to achieve with the pitch of the footprint. So a lot of times you might see a gang release more commonly used on flex for IC packages. Next, considerations for through-hole footprints that are placed on a flex design. So generally, you want to make sure there's at least a 30 mil annular ring oversize. This is good practice. There's not always space for it, but bigger annular ring, the better. And again, you also want to anchor those pads with either adjusted pad shapes or teardrops or anchor tabs. You can see in those bottom images a few different styles that I've seen in the past used to anchor pads to the board. And it just helps, again, prevent any peeling of the pads off of the board during the assembly. The next type of footprint to be really aware of when dealing with flex design is a ZIF connector. These are going to be generally worked into the end of a flex with a stiffener underneath, and they're going to be plugged into a connector on a mating board. And the cover lay should be mostly removed in that pin area. So you'll see here there's gold fingers with the cover lay pulled back and the copper exposed so that the part can install correctly into the mating connector. And there's also a call out here for stiffener. For these types of parts, you really want to lean on the data sheets and try to build it in as closely as possible to their recommendations, because they will give recommendations on the copper, the stiffener, the cover lay, the thickness, all of which are going to be very critical to build into your board and your fabrication drawings so that the part will install correctly. So this is just a note to remind you to double check those data sheets and really make sure you're building in all of those as close to spec as possible. Because if you're not building in one of these items, it could result in an issue with this installation. All right, moving on to placement. So when you're dealing with placement in stiffener regions, again, this is dealing with the flex area. If you're dealing with a rigid flex, placement is the same as always dealing with a rigid board. But if you have, like in this image, you can see the board is fully flexed, but there's a few areas that have a stiffener attached. There are some placement items you want to be really careful of when putting components on the flex. So when you have a stiffener, you want to make sure that any surface mount parts are placed on the opposite side of the board as the stiffener to make sure that you're able to install it on those pads correctly and the stiffener is not impeding any of that installation. But with through-hole parts, it's the opposite. You want to put those, as you can see on the right side of this flex, there's a through-hole connector. It's actually placed on the stiffener because the through-hole leads are going to go through the board and need to be soldered on the opposite side. And it gets very difficult if you're trying to solder them, but the stiffener is blocking your access to those pads. So there is a difference in how you want to place components when you're dealing with a stiffener. It gets a little trickier when you have through-hole and surface mount parts that need to be on the same side of the board. So this is possible. It just takes a little extra documentation. You can have them both on the opposite side of the board as the stiffener, but you do need to call out larger holes in your stiffener around those through-hole leads. So there is still an opening to access the copper on the bottom side of the pad to solder that lead. Otherwise, it won't be able to be installed correctly So it's just an extra step if you need to have both types of parts on the same side of the board. Ideally, you're able to get them on opposite sides. And again, there should be no parts or vias placed anywhere near a bend line. Bend lines are very vulnerable areas of a flex, so you want to just try to keep it to straight routing with no other items anywhere near the bend. Next, moving on to routing. So a few tips to keep in mind when you're routing your traces and pours. First is if you have traces on alternating layers of your flex, you want to try to stagger them to go in the channels between each other instead of having them directly on top of each other. Something like this might not matter on a rigid section, but since the flex is so thin and it's so flexible, it could create a bit of a weak point in your flex to have the layer stacked. You can see in those bottom images, the second image is much more evenly distributed and it's going to allow a better use of your flex. The traces should be also equally spaced. Again, you want to make the best use of your flex and try to keep it really consistent how you're designing across of it. And then also traces that are crossing bend lines should be crossing perpendicular to that bend line. Again, bend lines are really fragile. You've got to be really careful when designing around those. That's again why you want to make sure you know where it is at the beginning of the design, so you're aware of it at all pieces of the design process. A few more items on traces and pours. When you're dealing with flex design, you want to try to get curved traces anywhere instead of using a 45-degree angle because, again, the flexes are really fragile. You want to take out any sharp edges in your copper. And generally, we'll also see a hatched ground plane across the length of a flex. This is used to increase the flexibility. The more copper that exists, the thicker the board will be and the more rigid it will be. So if you're using your flex really because you need it to have that tighter bend radius and fit into smaller areas, having that hatched ground plane across the flex region will allow you to add a little bit of additional flexibility there. A few things to keep in mind with that, it does break up your return plane. So you can see here, there's a lot of removed copper. One of the reasons why you will generally see a hatch plane on a 45-degree angle like this, as opposed to north, south, east, west signals on a 90-degree, is because it allows a more consistent return plane for signals that are crossing the flex. If it was 90 degrees, then you might have some signals fully over a track of the hatch plane and some that are skipping over every single one, and that gives them different access to return plane and could create some noise in some of your signals. Having it on a 45 is going to have the return plane more consistent for all of your signals, so that won't be as big of a source of any issues in your signal integrity. And the flex being hatched is optional based on your flex requirements, but it's a very common use of hatched design. Next is a few routing tips for dealing with vias and pads specifically. So when you're looking at a rigid flex transition, there is a little bit of extra care that needs to happen because the materials transition between flex and rigid under that area as well. So you want to make sure that there are no holes, vias, or components within about 50 mils of that rigid flex transition. That number might be a little different fab house to fab house, so it's a good idea to double check once you've identified your fab house. But 50 mils is a good rule of thumb to keep the edge of your hole away from that rigid flex transition. Teardrops or fillets on pads and traces for via anchoring. Again, the same way that we wanted pads anchored, you would want any additional vias or pads on the board anchored as well. So those teardrops are very common to see across all flex design, just to, again, add a little more robustness. And when you can, vias should just be fully tented on the flex to protect them from peeling. Their flex is very thin, so having them fully tented doesn't really cause any problems. It just helps to protect them. And again, the bending area, try not to put anything there except for straight across traces. You don't want any vias in that area if possible, because it will just be more likely for them to break in those areas. The next thing I want to talk about is just how some of These design items are going to impact your rules and when you want to work with your fab house in the beginning to determine the right rules to build into your design to really streamline the whole process and not have anything kind of get you on the back end of the design. So first is the board edge clearance. Sometimes with Flex, depending on how they're routing out the edges, if they're doing it with laser versus mechanical, a laser cutter might have a lower board edge clearance, so you're able to get copper much closer to the edge of a Flex. Again, that's a question you'd want to ask to your fab house in their practices so you can build in that clearance correctly from the beginning. The next would be the minimum tracing space. As always, even with rigid boards, this a lot of times is driven by a combination of the copper weight and also the fab house capabilities. You can sometimes pay for a smaller tracing space with the more advanced capabilities. So make sure that is a question up front. Once you've decided on your copper weight, you understand their tracing space, minimum tracing space you can use in your design. And then the next is controlled impedance. Controlled impedance is possible across a Flex. It just takes a few extra specifications that you need to go through. So the Flex materials and the hatch plane will impact your impedance calculations. So if you have a standard calculator you're using for your rigid designs on rigid Flex, on rigid controlled impedance, then that's not necessarily going to be accurate if you want to get your controlled impedance also across the Flex region. I would strongly recommend just working collaboratively with your fab house on this. Make sure you're building out your stack up with them in the very beginning and they understand your controlled impedance requirements, and they're going to be able to give you a tracing space across the Flex region, depending on whether you're using a hatch plane or not, depending on how many layers your Flex is and what types of materials are being used. They'll be able to give you a modified tracing space to help keep that impedance as close as possible. So for example, I wanted to show what this might look like. When you cross from a rigid to a Flex transition with controlled impedance, it might look something like this, where the tracing space actually drops and changes as you go across that Flex region, and you'll see a little more clearly here. That will help you keep the impedance of those signals as close as possible. You don't want to just assume that you can use the same numbers you calculated on your rigid section through the Flex section. Again, it depends on what speed you're running it at, but for critical signals, you want to take a few extra steps to make sure you're meeting that impedance. And the last thing I want to talk about here is just the importance, as I've been discussing, of early Flex Fabricator involvement. So if you have never done a Flex design before, this is when it's most critical because there are so many specific items a fab house is going to give you in terms of their capabilities, their materials, their thicknesses, their bend radius, their recommendations for different via technologies. All of that should be built in from the very beginning. So if it's your first time trying a Flex design, do your best to try to find one or two potential fabricators early and engage them in the development of your design. If you've already been working with a house, you probably know the requirements now and have it already built into your designs. But it is more critical in Flex design than generally it is in rigid. Rigid can sometimes be passed to multiple fab houses a bit easier with less differences in their capabilities. So you just want to make sure you're engaging them early. Make sure all of the necessary departments are also involved. So it's not necessarily just going to be the electrical team to the fabricator. The mechanical team and any management might also want to be involved in those conversations because there are a lot of trade-offs that can happen at different levels of the design. And having everybody involved will really just allow you to find creative solutions that will save you time and money in the long run. So looking at each of those three groups I mentioned, the electrical, mechanical, and management, here are the items that they might have some opinions on in discussing with the fab house. The items I've highlighted in red are more applicable to this webinar here. The one that's happening in just over a week are the items that are grayed out here. They'll be talked about more in that webinar. But again, the electrical, you're going to be concerned about your minimum tracing space and your controlled impedance calculations and how the stack up affects all of those different items, maybe your current calculations. Mechanical is going to be a bit more, we talked about board thickness and bend radius, but those are really going to tie into your stack up development, which will be the topic of the next webinar. And management is going to be concerned about your lead time, your fab cost, and your design cost in general. So all of those things, you'll want to have that discussion at the beginning to just be able to kind of brainstorm and come up with your best solution. So just to summarize some of the main takeaways we've gone through here. First, you want to just determine the appropriate board type for the needs of your design, whether that includes flex now or includes flex down the line. There are some different trade-offs. Understand the differences in best practices for flex and rigid. Little things like curved traces and teardrops are going to be a lot more critical for flex. Check in often with all departments and collaborators, whether it's mechanical to figure out the flexibility you have, or the fab house to determine your stack up. The more you can keep open communication, the more you can stay on top of any potential issues, and just identify and communicate really early in the process instead of saving it to the end where you may have to redo some of the design work you had done. And that is my overview of flex design, and I will let Chris jump back in and take it away.
Great. Thanks, Lauren. That was fantastic. A lot of questions coming in. You sparked a lot of discussion, so hopefully we have some time for some lively Q&A at the end. Next, we're going to jump over to Matthew, and he's going to show you how you can use your CAD tools to help you apply some of the principles that Lauren had just gone through about flex.
First, just wanted to thank Lauren for that great presentation. A lot of valuable information passed along there, new stuff for me, absolutely, that I learned as well. So that was fantastic. Thank you. What I wanted to do here is just show you how you're going to do some of those things that she mentioned in her slides, how you're going to do them in your CAD tool. What I'm going to be focusing on is the Presto tool, which is hopefully visible for you here on the screen. Presto, in case you're unfamiliar, is the new user interface for the Allegro PCB Editor tool. The Allegro PCB Editor tool still exists and is going strong. This new interface is aimed more at new users, people that have never used the Cadence PCB tool before, or perhaps people that have come from competitive software into our environment and find this more attractive solution. So that's the purpose of the Presto tool. That's the people that we're trying to target with, is really just new users and those that have experiences with other tools that might prefer something like this. So I'm going to be using this tool for the demonstration. We could just as well be using the other tool, the classic PCB Editor tool, the one that many of you may know already. We're going to be working in this one though today. What I want to start out with is actually comments. So I'm going to show you the commenting system in this Presto tool. It also exists in the classic tool as well too. So you can go here to comments and you can start typing out new comments, which are going to reside now with your board file. So as you pass this from your company maybe to a contractor that's working on it, you can put comments in here, draw attention to areas that may need some work, and then you can comment back on those. So in my case, I just made a comment here, verify stack up, view ground. So I'll just do that really quickly. I'm going to take a look at my ground, which happens to be on layer 1. And this board is really similar to the one that Lauren had drawn up, showing some different regions. I have a rigid region over here on the left and the right, and then a flex in between, joining those two rigid regions. So that's my stack up. I have my ground layer going between those two regions. I can see the ground nets here are being called out, so you can see that right there. And I'll take a look at the stack up here quickly as well. So we can go here into the cross section, take a look at that stack up. I'll just pull it over to this screen. And here we can see the stack up. As Lauren said, we're going to spend more time in the subsequent webinar on the stack up, so I'm only going to touch on it briefly here. But what I have is the stack up that you're probably used to over here with your top, inner layers, and bottoms. But then what you can do also is add additional stack up layers. In my case, I just have the primary, so that's your rigid section, same as the all stack ups. And then I have a flex area, which is using layer 1 and layer 2. So reasonably simple stack up here, but you can have multiple that are available to you and see them all here, bring them all together. And once you have those stack ups defined, you're going to set up different zones where those stack ups are going to be applied. So just to kind of close the loop on this commenting system, I can say, done it. You can just write something in here like done it, like that, and submit that. And now that's part of the board file itself. When I pass this design file back to whoever I got it from, they can see my notes that have been added here to the ones that were originally there. And you can make new comments, etc., if you'd like to. Really nice system of passing notes back and forth. The other nice thing that I didn't mention is that you can actually click on this and you can see a picture. It's a little bit small, but you can see a picture of what the original commenter was trying to draw attention to. So if it's a small area, it's going to show you a little picture of exactly what that is going on there. Okay, so that's the design review. That's a look at the stack up, a look at the ground planes. And we can also take a look at this crosshatch section right here. So Lauren had mentioned that for flexibility of the bending area, we want to have that crosshatched. And you can specify what that's actually going to be crosshatched like. So you can just click on it here, and then in this Presto tool on the right-hand side is where everything is. So whenever you click on something, all the context for that element that you've selected is available on this right-hand side. So first off, I can see here that's on layer 1. I can see that it's tied to a ground conductor, so it's going to be tied to that ground net. And here's where I can set up exactly what that crosshatch looks like. If I have it just set as solid, that's fine. But I've come over here to crosshatch. You can choose how you want this crosshatch set up. In my case, I said diagonal both directions. So I'm going to get the diagonal up, down, and the other direction as well too. You can do it horizontal, vertical, the north, south, east, west that Lauren was talking about. Not quite as ideal because your return path might line up on top of a return line or off of one, which is going to change your impedance pretty radically. You can change the spacing here. These fields are dynamic. You can change them right here. And there's a few more choices for reliefs and stuff like that that you can choose here. Okay, so that's my crosshatch shape. And now what I want to do is I'm just going to route a net. I'm just going to take a single net from a component over here on the left over to my component here on the right. I want to kind of route it through this area. This starts on the top, this ends on the bottom, and this flex layer, as you remember from the stack up, is traveling on internal layers 1 and 2. So if I want to route this, I can just come into my routing command, and I'm going to choose to start on pins. So I'm going to choose pins right here. That's where I want to start. And then it's going to grab that, and I can start routing this net. So as I go through here, I can drop vias. I'm going to need to drop a via to drop to a different layer. That's going to take me down to layer 1. And I'm going to end this at I have a series resistor in here that I'm going to end that at. I just want to draw our attention to a couple things here. First off, we saw this as we transition to this flexible region, you can have your trace width change. So Lauren was talking about the trace in space. So this is your trace width. You can see that that has gone from something small to something larger. And you can have your spacing change as well too. I only have a single net, so you can't see that. But you can have that change automatically. The way you do that is with region rules. So let me show you those region rules associated with that shape right here that we have. So I'm going to go and highlight this region shape that I am going over right here. And that region shape is going to have, excuse me, it's going to have a constraint region rule associated with it. In this case, the constraint region rule that I'm looking at is called flex_rules. And if I go to my constraint manager, I can take a look at my region rules, and I can see that rule being shown there, and you can see the rule associated with it. So here I am in physical, I'm in my region rules. Here's my flex_rules. And you can see that I have some different widths associated with this one as opposed to the default board. And this is where Lauren was saying you're going to be talking with your board manufacturer. You're going to be having those early conversations with them to determine what some of these rules should be. And then you can just enter them in here. There are calculators that you can use to figure out some of these numbers, but the recommendation would be to talk to your board house because they're going to have probably a better understanding of their specific process and what the impedances are ultimately going to end up like. And if you want to match those impedances, they'll tell you which widths and spacings you're going to need to make those work. So that's where you can enter that flex rule. And let's go back to, well, I'll just show you one other thing here before I continue. This one right here, you can see there's this DRC right here. That's this bow tie or butterfly that we're looking at there. If we take a look at that DRC, what we're actually seeing here is we're seeing an inner layer spacing constraint error. This also is set up in our constraint manager. I'm not going to show it to you right now, but you can have spacing rules for vias to, in my case, transition zones. So this shape right here, it's maybe a little bit tough to see, but you can see a shape right here. That's our transition zone. That's transitioning from rigid to flex. We want to make a zone area saying that we want to now create rules to that area to keep things out of it. Just keep some of these sensitive items like vias and parts out of there. So in our case, this one's too close. It's got no space, it's got no gap, and we want something more than that. So you can come here and I'm just gonna take this via and I'm gonna move it, and that's gonna take it and put it somewhere hopefully safe. You can see that DRC goes away. So that butterfly or bow tie that we were seeing there has gone away, and that rule or that rule that we were checking against is now fixed. I can continue writing on the other side. I'm not going to do it right now just because I'm a little short on time, but what I'm going to do instead is show you also those teardrops that you can make. So if you want to make those teardrops in this tool to just give a little bit of strength to those connections, you can do that here as well. So from this tool, we're going to choose the teardrop, and there's all kinds of settings you can choose to make this exactly how you want it to come up. In my case, I'm just going to leave the settings as they are for the time being, and I'm just going to click on that component. You can area select over components as well too. You can have vias selected. You can have pins selected as well too. So if you want to put a taper on that pin or a teardrop, you can do that as well. If you want to teardrop on your sending pin over here on the region section, you can do that as well. So really easy to set those up. You can just click on the pin, click on the via, you can area select over them as well too. And if you ultimately want to remove them, you can just hit the remove button and get rid of them. So really nice way and quick and easy to provide a little bit of additional strength to those signals. Okay, so we saw DRCs on there. Let's set up a bend next. So the next thing we might want to do here is set up an actual bend. Right now I have this region defined as flexible, but I need to say, okay, where and how do I want to bend this? The way that you do that is under setup flex, we're going to create a bend right here. And you're going to just draw a line wherever you want that bend crease to kind of be. So I'm going to draw mine just right here. I'm not being too specific about it, but I'm going to specify that it's right there. And then as before, we get all the properties over here on the right-hand side. You can give this bend a name if you want to. You can modify the XY position of that line. You can choose where it's going to bend. Is it going to bend up towards the top, or is it going to bend down towards the bottom? So that's what this side here is. What's the radius of that bend? So Lauren was talking about how you come up with that radius before. I'm going to pop in 50 here. What's the angle of that bend? So how far can we bend it? Is it 90? Is it 180? Something in between. I'll say it's going to be 180. And you can also do a package keep out range here as well too. So if you want packages to be at least 100, I believe this is mils away from that, you can specify that, and you can maybe see it's a little bit challenging to see, but there's kind of a darker area right here. That is your keep out area. You can see that component is in it, and we're going to get a DRC here because of that. So that DRC is popping up because it's too close to that bend area. We could do a couple things to fix this. We could reduce the requirement if that was a possibility to something like 50. That should fix it. We could change the bend radius. We could change the location of the bend. We could move that component out of the way. Lots of ways of fixing that. If you want to view what this bend is going to look like, you can go into the 3D viewer, which comes up here. You can kind of spin this thing around if you want to, and you can bend the bends that you have. So as you as you take this thing, you can bend those and see exactly how that works. You can kind of look in between here and see what's all happening with that. So you can play around with that bend and ensure that it's going to work for you correctly. Okay, the final thing that I wanted to do, I am short on time here, so I'm just going to do one more thing, and that is just show you a slightly more complex board. This board I was working with here is pretty simple, not a ton to it, just kind of wanted to show some of the basics. And what I want to do next is I want to take a board that's slightly more complex, and you can see here there's a little bit more going on. If we take a look at the stack up, there's going to be some more stuff going on here compared to the other ones. So we'll view the cross section. You can see there's more different types in this stack up. There's some stiffener regions, some rigid regions, some flex regions, all kinds of different regions in play here. What I want to focus on though is the challenge of routing some of these things. So when you're routing down flex, you want to keep your routes as neat as possible. Lauren was saying we want them to be rounded just to provide a bit of strength. Those corners are going to provide areas where fatigue and breakage could happen. So we want to route our nets as nicely as we possibly can. So I'll just show you one way that we can do that, I think a pretty nice way. And then we'll pass it back to Chris for polls and questions. So let's add a connect here. And I want to route on my inner layer. This flex channel happens to be on inner layer 1 and 2. And what I want to do here is I actually want to contour this. So I'm going to take this trace right here, and I'm in on inner layer 1 right now. So that's where we're routing down this flex channel. But what I want to do instead of just traditional routing is I want to contour this to an object, and I want it to come off by, I'm going to say 0.25. I think this one's millimeter, this design. So I'm just going to click on the object that I want it to be contoured to. In this case, it finds the route keep in. So I'm going to click that, and now it's just going to travel along that with the constraint spacing that I specified there of 1/4 mil. So as I kind of zip along this contour here, you can see it hugging along that edge there really nicely. So instead of having to do a challenging route here where that's going to be pretty difficult to make that all work, you can just tell it to hug that border. And then once we're ready, we can come off here and we can end our connection like that. So really easy to do that. You can continue this way as well too. So Lauren also mentioned that it's good to kind of stagger your traces, not to have, if you do have 2 different layers, not to have them right on top of each other, but to kind of offset them a little bit. We can do that as well too. So if we want to now route the next one on inner layer 2, we can say, well, this one I want to have 1/2 mil away from the last one. So you can select that. You can come up here and you can choose that border again, and now you can just come around this flex channel, and you're going to be doing exactly the same thing. Just coming around there, it's going to be hugging that contour, and you can just finish making that connection. Okay, so that's everything I wanted to show you guys today. I'm going to stop sharing my screen, and we'll take some questions as we're able. Off to you, Chris.
Great. Thank you, Matthew. That was really helpful to see how all that can be implemented and how the CAD tool can help you keep track of all the different rules and assignments you need to have with the Flex design. I think we have a little bit of time for some Q&A. So if you haven't already, you can pop out the question panel and you can start asking some questions, and we'll start seeing if we can get Matthew and Lauren some questions they can answer. So I think first one I have on the list, this one might be one for Matthew, is can contour routing work with multiple nets selected?
That's a good question. I believe so, yes. So you can have multiple nets selected and you can route them along that way. It's going to work. I don't think it's going to work on staggered layers like I had shown here, but you can choose the ones that are on particular layers and route those at one at a time. So one layer at a time is kind of what I mean, not one signal. You can do a collection of nets on one layer. So yes, that should be possible.
Great. We had another one from Stephen asking, what is the max copper weight for Flex? I don't know if there's any one golden answer here, but maybe some guidelines you guys can provide.
I'll let Lauren take that one. The software doesn't have limits, but there probably are some practical ones, so Lauren can address that, I bet.
Sure. I have seen some requests for higher copper weight on flexes. The reason I recommend against that is usually because when you want to use flex, it's because you want it to bend. And as soon as you go higher than about an ounce, you're not really going to get much of a bend. So I have seen requests for 2 or 3 ounces on flex layers, but usually people decide against that because it defeats the purpose of what they're trying to achieve with that flex. So best practice is going to be to stick in the 1/2 ounce to 1/3 ounce area to get the most flexibility. And then again, that comes to, okay, does flex make sense in this scenario in the first place? If you do need high copper weight with loss of current, flex may or may not be your best option in those scenarios because you're really going to jeopardize the flexibility of it.
Thank you. Yep. Let's see. We have a number of people asking if they can get a copy of the presentation. Answer is yes, as well as we will send out the recording as well for those that may have joined late or have others that they want to share this with. What would be the smallest number of layers for a rigid flex design?
So for flex, you can strictly a flex section, you can do a 1-layer flex. That's pretty common, 1 or 2 layers. Again, you can go 3 or 4 layers, but the higher layer count, the less flexibility you get. In terms of the rigid portion of that, you can do, I don't know if I've ever seen a 2-layer rigid. It would probably be, if you're going to do a 1-layer flex, it would end up being a 3-layer rigid because you'd have 1 middle layer and 1 top and 1 bottom. But it can just go down to 1 layer with no problem. Those are very common.
Got it. Thank you. There was a couple of questions just around general, I think, Lauren, you went into kind of what are some of the consequences of using flex, but people asking when to, what are the advantages of going with flex versus just using maybe multiple boards with connectors and cables?
Yeah, so one of I saw that question there, and really the biggest benefit I've seen to flex, there's a few things, is when you have a really size constrained area, like within a cell phone, you'll see a lot of flex designs because they're trying to make them as small as possible, because it allows you to remove those large connectors that can take up a lot of space and large cables that sometimes can be a little cumbersome. So that is a really nice benefit of flex, is it allows you to really compact your design into a very small space. And it will also save a little bit of the cost and time that goes into assembly without needing to plug in as many cables or connectors that are required. It just makes it harder to debug. It makes it more expensive. As soon as you have an issue with your flex, you can't just replace the cable, you have to replace the whole board. And as soon as you have a ECO that needs to happen on one of the pieces of the board, you need to spin the whole thing because they're all connected together. It's not separated by a connector. So there are definitely trade-offs, but I would say the biggest benefit is just getting it really compact into a much smaller area.
Got it. Thank you. This one from Aaron is asking, do you have to do a hatched ground plane? I'm assuming the answer is no. There's just some advantages potentially to doing that, correct? For the flex cable portion?
Yep. You do not have to do it. It is meant to help with flexibility. So it's just one more way of getting more flex out of your flex, but you do not have to. I have seen people go with solid ground planes when they know they're not going to have an issue with that bend radius to help with any, return plane or controlled impedance. So that's just an optional thing to have in mind if you need it.
Got it. And then another one on, is there any, benefit or concerns for like a potential high vibration environment such as automotive when choosing flex versus, say, cables or something else?
Yes, that is a good question. I would assume, I haven't done an automotive application of flex, but flex are very fragile. So that when they're in sort of those more aggressive atmospheres, there's probably more of a risk there. They need to be sort of really solidly packed into their device. So it really depends on what part of the automotive application it's going to be in. Mm-hmm. So I wouldn't be surprised if there are some scenarios based on just the design environment and what part of the application it's in, that a flex may or may not make sense due to those, vibrations and other sort of environmental, dust and temperature and all of that.
Gotcha. Makes sense. Here's another one that may or may not have some insight into is there any kind of guidelines on, if you're going to have an area that's going to bend a lot and repeatedly, is there kind of like a fatigue factor for flex, or you go with cables instead if you're going to see repeated bending, or is that not necessarily a concern?
I don't know any rules of thumb off the top of my head for this, but it is something to be aware of. How many times is this going to be, maybe installed and uninstalled, and does that impact the types of materials you might choose, or your fab house might be able to guide you towards more reliable or robust materials in choosing the flex that would still work with your bend radius or the different cover lays, things like that. In the next webinar, I'll also talk about things like epoxy bead that will help save your rigid flex transition and prevent it from tearing. So there are ways that you can create it to be a little more robust, even if you know it's going to be flexed a lot of times. But that would come out in testing. If it's something that's, ripping constantly because of the wear and tear on the device, then it might not be the best implementation for flex. So they are very fragile. They're helpful in a lot of scenarios, but they're not going to work in every scenario.
Got it. And then maybe we have time for two more. One is, can you add a stiffener, or I would assume any of the other kind of flex unique stack up materials? Can they be accounted for when you're running simulations? Maybe this is one for you, Matthew.
Yeah, so when you're running simulations, so if you're using one of the Sigrity tools, you can definitely account for the stiffeners and those materials in your stack up, and they will be considered when you run extraction, so yes.
Great, thank you. And I think this will be the last one. If any comments or general guidelines if you're trying to build a panel for a run of flex boards that you would look at, as opposed to just standard rigid boards?
That is a good question. I would recommend working with the Flex Fabricator on that. They're much more well-versed in creating panels, whether it is rigid or flex boards. They'll be able to help you optimize your panel and let you know what callouts you need in your fabrication drawing to be able to maximize your use of the panel. So you can definitely panelize, but that is one of those areas I would recommend that collaboration and allowing the fabricator to give you input on what they like to see in terms of their spacing requirements and route keep outs and things like that.
Got it. Thank you. All right, I think we're at time. Just want to once again thank our presenters, Lauren and Matthew, for doing a great job. Very kind of deep topic, and I think they covered a lot of ground today. And thanks for everyone for attending. And as I mentioned, we will send out a follow-up with recording and presentation. And if we didn't get to your questions during the session, we will get back to you afterwards. Thank you very much. Have a good rest of your day.
Thank you, everybody.